In our last video, we introduced the idea of continuity by just building up some basic definitions. But what we don't have yet are some practical ways of actually using those definitions of continuity to describe the continuity of functions. So we want to build up some properties. Basically, we're going to start off with the general idea and definitions, remind ourselves of what that means. And from there, since the idea and definitions of continuity are relying on limits, we'll be able to use some properties of limits to connect a bunch of functions with continuity. So we'll be able to describe functions pretty well. We'll talk about polynomial, rational, and transcendental functions, how continuity works with them, and then we'll end things off with talking about composition, which is a new operation that we haven't talked about yet. It's not new to you, but we haven't talked about how composition works yet with limits or anything like that. So that's where we're at. So the first recap, what does it mean for a function to be continuous? This is our main idea here. The limit as x approaches some value a of our function is equal to the actual function value. We'll remember that this is talking about continuity at one specific point. We also could say, even if this doesn't work, we might have a left-sided continuity where the left-sided limit is equal to the function value, or a right-sided continuity if the right-sided limit is equal to the function value. But the end goal is that hopefully we can talk about two-sided continuity. We talked about the definition of an interval of continuity. It's just if this definition of continuity is true for all the points in an interval. Now, we didn't actually talk about how to find intervals of continuity, so that's what we're going to build towards in this video. So here are a whole bunch of different properties of continuity. Let's give a little brief intro to this and we'll read through some of this stuff. If we have two functions that are both continuous at the same point a, then all of these combinations of those functions are also continuous at a. So if you take those two functions and add or subtract them together, they're going to be continuous at a. Why is that? Well, it's pretty obvious when we write it out. The limit as x approaches a of f of x plus g of x, this is equal to the sum of the limits. I'll do this one time, and then we won't do it for any more of these. If both of these things are continuous, then we know that this is actually f of a plus g of a, because both of those are continuous at a. And so again, by our definition of continuity, the limit and the function value are the same thing. And then you can say, oh, look at that. That's the same as if we just evaluated this sum of functions at a. So sums and differences work out really nicely. You can do the same thing with products. No difference there. Coefficients on functions act the exact same way. So if you have some constant multiple times a function f, that's also continuous at the same x value a. If you look at a quotient of functions, that's going to work. The only problem is if you divide by 0, because then limits of quotients have problems. They're not the same as just the function values in this case. So as long as we're not dividing by 0, we have continuity at a. You can raise a function to a power, and it's still going to be continuous at that same point a. You can take a root of a function, and it's still going to be continuous at that same point a. The only problem with roots is that if we have an even root, like a square root or a fourth root, we're not allowed negatives under there. And so we need to look at our function being positive. You might say, well, can't our function be positive or equal to 0? And that's kind of true, but kind of not. It's possible that we have continuity when the function does equal 0 underneath that root. Here's a quick little sketch of what I mean. If you have a function that looks like this and you take a square root of it, everything around this point is positive, and so when you take a square root of this, you're going to have nice positives on either side of the 0. But if we had a function that looked like this, and you took a square root of it, oops, I missed the point here, then sure, our function is equal to 0 at this point, but since it's negative around this, when you take the square root, we're going to have a whole bunch of non-real stuff, and this single real number won't be connected to anything. Continuity is all about connectedness of our function. And so that's why we don't just say greater than or equal to 0. We do need to check those spots where our function is equal to 0 specifically to see if we have continuity, possibly on one side, possibly on both. But either way, we need to check. Okay, so let's get into some actual specifics. Let's see if we can talk about intervals of continuity for some specific function types, polynomials, rationals, transcendental functions, etc. Here's the big idea for polynomial and rational functions. We built polynomials out of constants times the variable x, raised to exponents and all that stuff. But really, it's just these constants and identity functions combined together using operations. So as long as we can show that every constant function is continuous on the interval from negative infinity to infinity, and that the identity function y equals x is also continuous from a negative infinity to infinity, then when we use these operations to combine them together, if they're both continuous at every real number, then the combinations of them will also be continuous at every real number. That's not going to be too bad. All right, so let's just do this. Let's show that the limit as x approaches a for f of x is equal to f of a. So I want to show this for f of x equals a constant and f of x equals x, the identity function. Let's do the constant one first. This is the limit as x approaches a of k. That's a constant. We know that's k. And also f of a is also k because it's constant. And look at that. They're equal to each other. So the limit as x approaches a of f of x is equal to f of a. Check. Continuous at a. And that's going to be true no matter what a is, right? For any real number, a. So there we go. Negative infinity to infinity. Let's do this one now. We're going to try the limit as x approaches a of x, and we'll see that that's pretty clearly a. And then we'll also say that f of a is a, and look at that. They are the same. So the limit as x approaches a of f of x is equal to f of a. And again, this is true for any real number a. And so we have these intervals of continuity for both of these function types. Now you can see how this is going to work. We're going to combine all these together to get polynomials in the same way that we did when we were evaluating limits earlier. And we're going to notice, hey, polynomials, you just spit out the function value. That's a result that we've already used, though. Limits of polynomials are easy. You just evaluate the function. So what we can say is that polynomial functions are continuous on the whole interval of real numbers, from negative infinity up to positive infinity. That means that rational functions also are going to be continuous as long as we don't divide by 0. Because again, in the above set of properties of continuity, we said that if you divide two functions that are continuous at a, they're going to be continuous as long as you don't divide by 0 at a. Now, if that means that both of these functions are continuous everywhere on all the real numbers, the whole combination of them when you divide is also continuous on the real numbers as long as you don't divide by 0. Easy enough, right? So let's check this. Let's find an interval of continuity, or maybe we'll say intervals of continuity for this function. Intervals of continuity. Continuity. I'm having a hard time spelling today. There we go. All we need to do is look and see, where do we divide by 0? Well, pretty clearly when x is equal to -1, and pretty clearly when x is equal to 4. So our intervals of continuity are going to be negative infinity up to -1, -1 up to 4, and 4 up to infinity. I'm not going to use the union sign in between here because it's possible that we get a function that looks like this, where our intervals of continuity are like negative infinity up to 4 and 4 up to infinity. I don't want to union these sets together because we only have one-sided continuity at this closed endpoint. So I'm just going to list these intervals separately. We're continuous on the interval from negative infinity to -1, from -1 to 4, and from 4 to infinity for this function. Notice that even though we don't have a vertical asymptote at -1, we still have a spot where our function is not defined. So it still breaks this idea of continuity. All right, that's not too bad then. Let's think about inverse functions. I'm not going to prove anything fully here, but I will give a little sketch to hopefully see what's happening. So I want to draw a function, and I'll just try and draw some function that's 1-to-1, meaning it passes the horizontal line test, right? So maybe it does something like this. I'm going to try and draw an easier function for me to sketch. I'll do that. That's pretty good. Here's my function. If we say that a limit exists, then that means at some point A, we can trace this thing up and find some point L where we have something happening here. Specifically, what we have is that for some interval of y values, where we're saying like these are the y values that we're defining as close to L, arbitrarily close, we can trace these things back and find a corresponding interval of x values. All right, so all the x values in this interval will spit out the interval of y values that we said were close to L. Now, for a one-to-one function, what you'll notice is that this picture kind of gets preserved. For one-to-one functions, you can find an inverse of that function by reflecting it across the line y equals x. So I'm going to draw a green function here. Oh no, I got my straight line tool on. Here we go. I'll draw my green function here. It's not going to be perfect, but it'll be okay. And it's going to look like that. That's kind of like our inverse function, we'll say. What we'll notice now is that this is what a used to be. So I'll call this L, but really it was old a. And over here, this is a, but it was our old L, because we flipped these things, right? And you'll notice that these intervals still get preserved. So if we could find the interval no matter what in the regular function, then we can always find the corresponding intervals in the inverse function, because they're going to change in the exact same manner. Hopefully that's a helpful enough picture to see. We can still get close as we want to this point by just changing which variable we're moving on this blue graph. So if a blue function is continuous on an interval, then the green inverse function is also continuous on that interval, because limits and function values are going to match up exactly the same way. All right. And notice, sorry, it's not the same interval. It's the corresponding interval, right? Because this interval got moved down here because we switch x's and y's when we invert functions. So corresponding intervals. All right, so what that means then is that if we think about sine and cosine as functions, and I'm just going to tell you that these are continuous from negative infinity to infinity, you could investigate them and probably believe me. If we just think about how these things work, if you go around the unit circle, our outputs are going to change very, very smoothly. I shouldn't say smoothly. I want to say they're all connected to each other. So if you think about like a bad idea of continuity, you could draw the graph of sine and cosine without picking up your pencil. Not a great definition of continuity, but hopefully intuitively we know that these functions are continuous everywhere. That means that tangent and secant and cosecant and cotangent are continuous on their domains. Notice all of these have division in them. So wherever you don't divide by 0, they've got a bunch of asymptotes, so just move around those. But also all the inverse trig functions are also continuous on their domains. Also, we'll say any exponential function is continuous from negative infinity to infinity, its whole domain. And log functions, the inverses of those, are continuous on the range of the exponentials from 0 to infinity. So on their whole domains. The last thing that we'll talk about is composite functions here. Let's say we have two functions where g is continuous at some input a, and f is continuous at, this is supposed to say g of a. Then the limit of the composite function is going to just be continuous at a as well. Or sorry, the composite function will be continuous at a. Even if g isn't continuous at a, if you know what the limit is in there, not the function value, then you can still go ahead and trace these limits through. What this means is that continuity helps us deal with composite functions and limits because it allows us to move this limit inside a layer of continuity, a layer of composition. We've had this explained to us for certain types of things. We're able to do this for square roots, right? We're able to do this for certain things like that under some conditions. Now we're going to say, in general, you can always move limits inside a layer of composition if we have continuity on that layer. Let me show you what I mean. So what does this say? It means that if we want to either find this limit or find these intervals of continuity, we can think about this composition pretty easily. Let me maybe start with the second one here. If we want to find this limit, we'll say this is the same thing as the limit of the quotient, e to the square root of sine of x plus 1 over the limit as x approaches pi of x cosine x. And what we'll say is that the exponential function is continuous everywhere. So whatever this is in the exponent, as long as it's a real number, we can scoot this limit up on the inside. Meaning we've got e raised to the limit as x approaches pi of the square root of sine of x plus 1. And we'll notice that the square root function is going to be continuous as long as there's no negatives underneath. So we can scoot that inside as well. You'll notice all of this to say is that we can really just say, as long as there's no problems of continuity, no division by 0, there's no negatives under square roots or things like that, evaluating this limit is as easy as just plugging pi in for x. You can trace this through and find this to be the case. So all this to say, you work pretty hard and you can get to e to the square root of sine of pi plus 1 over pi times cosine of pi. Sine of pi is 0, so this is the square root of 1, so this is just e to the 1 over pi times negative 1, so negative pi. So this limit is negative e over pi. And that's easy to do because, even though this looks complicated, all of the composition that we have preserves these limits because we have continuous functions at these points. Similarly, we can think about intervals of continuity. We know that our log function is only continuous here for 0 to infinity, which is good because our square, or our fourth root, wouldn't be able to take in any negatives. So this is only going to be positive. We're also going to notice that x can't be negative 2 or positive 2. Now the negative 2 doesn't matter because we're looking at this interval already from 0 to infinity. So what we can do is say from 0 up to 2 and from 2 to infinity. Now what we can also do is try and think about one-sided continuity. Do we have one-sided continuity at either of these spots? At 2, we have a vertical asymptote, meaning the function value does not exist, so no. At 0, we don't have any one-sided continuity because we have an asymptote on the log function. It doesn't exist. So no one-sided continuity here. Open intervals of continuity. All right. Hopefully that's helpful to see. What do we got to do now? Well, there's still more about continuity coming. The big result from continuity, the big important thing that we're going to string through the rest of the semester is called the intermediate value theorem. And you may have seen the intermediate value theorem slightly before, but we're going to go a little bit more in depth into it probably. And throughout the rest of the semester, we're going to have a lot of situations where we're going to say, okay, as long as f is some continuous function, these results are going to hold true. And most of those are going to be because of the intermediate value theorem. So we're going to see this result that we're going to talk about later on show up over and over again. It's going to be an important result for the rest of our time studying calculus. So that's what we're going to push towards. And then we'll be finished with continuity after that. So hang in next time, intermediate value theorem. It's a really fun topic to think about, and it uses this big idea of continuity.